We all set then? Perfect. Today I'm going to be talking to you about how we can interpret historic lake levels from the internal architecture, the internal layering of a coastal deposit. And the coastal deposit I'm going to be looking at is the Grand Island Tombolo. I'd like to start out by thanking ORSP and SRU for helping to fund this project. The United States Geological Survey, Pictured Rocks National Lakeshore, Grand Island National Recreation Area, and all the other previous researchers who have done work along the coastlines of the Great Lakes. So where we're looking at is Grand Island, which is right here. It's just a couple hours to the east of Marquette. It's the largest island on the southern shoreline of Lake Superior. It consists of two bedrock lobes, these high topographic highs there, and they're connected by the narrow Grand Island Tombolo. Tombolo is a coastal depositional deposit that connects two lobes of bedrock. This specific feature we're looking at is a sandy Tombolo. And then just some other facts about the area. We're right adjacent to the Pictured Rocks National Lakeshore. And then we also have Beaver Lake up here, which I'll be talking about a little later in the presentation. So what that looks like from the mainland is we have the two bedrock highs right here. And then between them we have the sandy Tombolo, which doesn't really appear in the picture. It's only a couple meters above the current lake level. Here's a more zoomed in image. The transect we took across the Tombolo is labeled right here. To give you an idea of what that looks like, this is from the southern end of the Tombolo. The southern end is a little lower, so it's more inundated by water. The northern end is higher and more subaerially exposed. And so our technique we used was called ground penetrating radar, GPR. GPR is a non-invasive way to image the shallow subsurface. And how it works is it sends radio waves into the ground, which rebound off layers of sand that gets deposited over time. It's essentially the same as sonar, except instead of looking through air or water, we're able to look through sediment. Now, how we tell the velocity of the wave through the sediment, so we can get at depth, is we take a CMP. This upper line here is the wave traveling from one antenna to another through the air, and then the bottom wave is it as it travels through the ground. What that looks like in the field is we have a computer with our batteries and everything we need to power the unit attached to a transmitter and receiver antenna with a set of fiber optic cables. In addition to ground penetrating radar, we collected topographic data using TopCon laser level so we could adjust our profiles to changes in relief. The data, when it comes out, looks like this. This is the east-west line we took, so it's perpendicular to it's parallel to the shoreline. And it consists primarily of horizontal lines. The really cool part of this data is the north-south line, the line we shot clear across the entire Tombolo. This top one here is the process data, and this bottom one is interpreted. Of course, you guys can't really see that, so I'm going to talk about these two sections. The first section I'm going to talk about is this one on the northern end of the Tombolo, so this one's slightly on the higher end of the Tombolo. What that looks like is I identified two units in it, this upper unit and this lower one. Both consist of northward dipping horizontal continuous reflections, and the main difference in thickness. I interpret this unit, the top one I interpret as the modern strand plane, so this would be the subaerially exposed portion of the Tombolo, the beach essentially, and these lines of these dipping reflections represent this feature is prograding, building out over time. This lower unit also represents progradation, except this one was deposited below the water level. Now what's really interesting is the southern end of the Tombolo. We still have the same two upper units, the modern beach and the modern shore face, but we also have these two lower units. Now how I interpret this one is this third lowest unit, it's the same thickness as the modern strand plane and has the same reflection. So I interpret that as a historic strand plane, a historic beach. This lower unit I then interpret as the historic shore face. Except we can of course see that the modern shore face and the historic shore face are completely different. They don't look at all alike. So why is this? One theory I have that I'm rather fond of is that during winter we have the lake ice and then dunes migrate over the lake ice. In springtime the ice melts and the dunes fall into the water, which creates these reflections. Then during summer, through erosion, this surface is created. And through a repetition of this process, we're able to prograde out a beach face in a cyclical pattern. Now, of course the question comes, what else do we know? We have a well log taken from nearby the Tombolo, and what we can essentially, the key points here are we're only seeing down to a depth of about 25 meters, so we're all looking through sand. And we don't have any bedrock till we get about 80 meters below the subsurface. So there's a lot of stuff that we don't understand, and we're only looking at the top portion of it. We also have the paleohydrograph for Lake Superior, which is based off a drill core they took out of Beaver Lake. And how this paleohydrograph works is, this is 10,000 years ago, and this is today. So beginning 10,000 years ago, we had the glaciers sitting just north of Duluth and the UP. And we had a proglacial lake that was at about 200 meters. Now, as the glaciers retreated, this lake level drops dramatically to about 170 meters, which is a period of about 8,000 years ago. Then, because the ground is rebounding after you remove the mass of ice and climate change, the lake level rises up here to about 10 meters above where it is at present. During this time, Superior, Michigan, and Huron were all one big giant lake without any topographic changes in between them. And then again, because you have the ground rebounding at different rates, lake levels drop to their modern level. So, what we do is we plot the historic shoreline from about 8,000 years ago, and then we correct for elevation, assuming position 0 on the southern end of the Tombolo is the mean lake level, or 183 meters, and then plotting that against our inferred shoreline, they show a near perfect match. Therefore, I think we can safely assume that I'm interpreting this right as the historic beach and the historic shore face. But of course the question comes, where do we go from here? Now that's what I just told you. I would like to go back to this Tombolo because I believe we can tell 8,000 years of lake level history through one coastal deposit. If we map the high point of Lake Superior about 2,000 years ago, its shoreline follows this cuspit right here, Duck Lake. So I believe we should be able to tell 8,000 years of Lake Superior history from one coastal deposit. No one else has ever been able to find a deposit that we can do anything even similar with. So, thank you.
And now we'll have 5 minutes for questions and answers. So, does anyone have any? Yes?
On one of your vertical axes, it was time.
Yep.
Nanoseconds?
Yep.
So does that relay into, can you take that and relay it into like years or modern time, or is that just strictly for the
No,
sonar?
it's because when we shoot the wave through the sediment, we're measuring time,
Yeah,
and then we have to convert that into
to depth?
depth.
So it
That's why
doesn't-
we need to figure
okay.
out the velocity.
So that has nothing to do with like actual like years, like history?
No, we can use other techniques such as OSL, which is optical stimulated luminescence, and through those techniques we can tell when a quartz grain was last exposed to sunlight,
Mm.
and so that's more how we can get at dating. We can also do radiocarbon dating if we have
Yeah.
wood fragments or anything.
Okay.
Would this ground penetrating radar approach have value in accommodating climate change by looking at coastal deposits to figure out which areas are going to be more quickly eroded than others?
Yeah, I'm actually hoping to go to China this summer to do ground penetrating radar with Dr. Joel to look at tsunami deposits and storm deposits, which I believe is what you're getting at. But you can really do almost anything when you're looking at the shallow subsurface with this. It's just knowing what you're looking through. And another sort of drawback is it's very site specific. If you have any fine grains, any muds, any silts, the EM wave won't penetrate those, and so you won't be able to see through them. That's why it works so great on coastal deposits, because it's almost all quartz, and it penetrates quartz very easily.
Another question, I know that years ago, oil exploration off the coast used explosions. Is
Shallow
ground
seismic.
penetrating radar now kind of the gold standard for either offshore or onshore exploration?
Nope,
of petroleum?
they still use that technique called shallow seismic, and that will give you data for kilometers or tens of kilometers. With ground penetrating radar, we can only see at a max of about 30 meters.
Do you think there's any unconformities when, if there was erosion as well as deposition going on?
There should be, but we don't see that, and I think the reason we don't is because we have those two bedrock lobes, and then we have wind coming in from the northwest, and I think that's able to concentrate enough sediment, so even when you rise lake levels, you're still gonna deposit material in that area, which is why it's so cool.
Are there any further questions? All right, well, let's have another hand for our presenters.